We're recording. Okay, perfect. So, hey everyone, welcome back to the continuation of our TQFT series, and for this is the third one in the series. So in this one, I didn't put an abstract. Sorry about that. I was still trying to write down the notes, so I wasn't sure exactly what to put for the abstract. But the subtitle of this one's the Cobordism category, so we're mainly going to focus on that, which, if you remember from the first talk, is in the source of the symmetric monoidal functor, which is our TQFT. And so we're gonna explore what that is. So we've in the first one we talked mainly about category theory. Then in the second one we did braided monoidal categories and the braided monoidal functor. And now we'll talk about the cobordism category. This one should be a shorter one. I always say that, but it always ends up being the full amount. But yeah, we'll see. Okay, so the last thing we got up to was here for a we defined the braided monoidal functor, and we talked about symmetry, and we said, okay, so if it's braided or symmetric, we'll call it braided or symmetric monoidal functor. So some graphical calculus stuff that I didn't really get to at the end. So the very last thing that we talked about was if I have my functor on x, y, and z, we have this diagram, and here the indices should be x and y for the monoidal functor, and this is f x tensor y mu this is f of x tensor y tensor z, and this becomes, you use f of alpha, which tells us that we can re-bracket inside of this. We can't have, so this diagram is values in C prime. So I'll write it, here in C prime. Well, I guess I should go back to defining what C prime is. So, right, our monoidal functor is from C to C prime, right? And we have this diagram, and this is the natural isomorphism in the diagram we had. Now I'm kind of regretting doing this because I don't want to, there are things that I'm not defining here that I defined last time, and some people weren't here, so I'm thinking maybe just going back and doing that again, but might take more time. So maybe I should skip this. I don't know. Okay, I'll just finish this, and sorry if this isn't making too much sense. Kind of ended up at not the best place last time, so yeah, that's my bad. Mu, mu, and this becomes f of x tensor y tensor z, and these two diagrams are equal, which is one of the commuting diagram conditions that we had for our monoidal functors. Yeah. Okay. So, okay. Yeah, maybe I shouldn't have stated them. I should have stated this last time, but that's my bad. So, part of the graphical calculus is that I'm going to introduce new notation. So this is my f of x. I'm going to define this to be that. So this is f, this is f. I'll at some point omit the f and x. It's just implied that when there's an arrow, this is my category, and these are the two lines that squish this in between them are the functors. And so also f of 1, we don't draw anything, so f of 1 will just be this, because as we said last time in the graphical calculus part, ones we just don't draw. And the epsilon map, what it does is that, remember, it takes in 1 and it spits out f of 1. So there's a 1 here that we don't write down. And okay, so if I have this diagram, the thing we talked about last time, mu spits out f of x tensor y, and so these are my f of x and f of y. If I draw this diagrammatically like this is x, this is y, and what it'll look like is this. So I define that to be that. Just new notation should seem intuitive, and okay. Yeah, these things, yeah, tubes.
How do you distinguish like two lines that are is it just like if two lines next to each other is a tensor product?
Yes, yes. That was yeah. Sorry, I guess you weren't here for part 1 and 2. Yeah, if we part of the graphical calculus is that when they're next to each other, it means they're being tensor product with each other. Yeah, those ones. No, they just get close and just continue. Yeah, yeah. This makes them into one line when we have a mu.
Wait, but you're saying that this diagram is defined as this diagram?
Oh, sorry. Yes. Sorry. Yes. I don't have it here though. Okay.
At least you're joining them like at the top of the pants.
No. Okay. Okay. Sorry. I take that back. My bad. So yeah. What this does, what mu does, is take in these two and give me this. So x tensor y is it they should be next to each other, right? No, one thing. They're next to each other like this. So this is denoting to me x tensor y, and because I have the two lines around them, as I said here, it means I'm taking f of that thing.
So if you have two lines beside each other, then it's
Tensor.
product.
Exactly. So from here,
Should that be a definition then? Like of the, or is it,
yeah, definition.
but you're not saying how products work in this diagram language. You're just saying.
Oh, like the tensor product.
So like product is when I put two lines beside each other by definition.
Yeah. We defined this in the last talk. Yeah. Sorry, I guess I'm using a lot of things that did last time. Yeah, but yes, when they're next to each other, by definition, it means that we're tensor producting them together, or the generalized tensor product, which is the monoidal product. But I'll just say tensor to make it easier. And so, from what I said, wrote there, Here, what's this? There's an x and there's two lines around it, so it's f of x as we discussed here. Same here for the y, and what the mu does is
Mu puts a cap on the
it,
inner F.
yeah, exactly what I was just about to say. Yeah, it adds in this cap to the inner lines, inner, um, and makes this into one round thing. And so when you look at the output, these two lines are close to each other. This is x, this is y, so this is x tensor y. And because I have the lines around it, and these arrows just carry on, along the whole thing. These lines around it denote that I'm applying f to that thing. Okay. Good. Good questions. Okay. So, okay. Yeah, I didn't really think through the continuing on the stuff, just because I didn't end like at the end of a chapter or something. But there was a condition that we talked about. I should just find it and write it down because if I don't, I think it'll be confusing. There was a condition that I'm gonna rewrite using the new notation that I just mentioned. Just trying to find that. Oh, I didn't mark it down. Oopsies. Okay. Okay, maybe I can write it down, and then together we'll try to find what that condition was. I should have. So if you remember, it was we had some conditions that we denoted with asterisks or double asterisks. Well, one was triple asterisks, and I didn't put that down for the condition. But okay, so just take my word on this that the condition triple asterisks that we talked about can be rewritten in this new graphical calculus notation, which is, I'm sure we can find it. To do this, and yeah, do that, do this. Right, okay. So, this is my x, should be my x, y, and z, and this is, right, it should be that one. Yes, f of x, y, z. Okay, okay. Yeah, it should be that one, I think. Let me just write it down before I make any judgments. This should be equal to same thing but kind of flipped this way. So it'll look like go like this, go like that, and go like this. And okay. So here, first mu is happening first on between the x and y's, f of x and f of y, and then the output is being combined with the f of z with this mu later on. And this is saying this is the same as that one. So when we look at here, it's the same thing. This one is the left-hand side of this equation is the left-hand side of that equation. And the right-hand side is the right-hand side. So it's saying that, right, if I have my f of x and f of y, I combine them using mu, then the output of that is this thing, f of x tensor y, right? This is f of x tensor y. Why? Because this is x tensor y, and it's between two lines, so it's f of x tensor y. Then there's another mu here, which combines all three of these.
And then, like you said last time, we just don't denote the associator on the diagram because it's just understood.
Exactly. we don't denote the one associator's inverse of the associator, left uniter and right uniter, because they're implied. We can just recover them if we need to. It just makes the notation messier, so we get rid of them. The only important thing to note from last time is that in that diagram, because it's done in C prime, remember our functor, our monoidal functor takes in values in C and spits out values in C prime. The all the stuff that I just mentioned in C prime, we don't write them down because they're implied implicitly. But alpha here, we have to write it down because it's alpha is in the unprimed category. This whole thing takes in values in the prime category, the output of this diagram. But that's why I can.
Isn't this the reason you just need to have the alpha on top so the equality will
Exactly.
stay on the same thing?
Exactly. Yeah. So this step I have to have it because I can't just re-bracket something that's inside of the F. If it was outside, if it was like this bracketed with something else that takes in values in C prime, then yeah, I could re-bracket it without writing it down. But yeah. Okay. So this is that one. I guess I should mark this and also put it in the notes as well. This is the triple asterisk condition. Okay. Now, okay. Once we get to the Cobordism category stuff, it'll make more sense because it's new stuff and I won't be using a lot of stuff from older talks that people might not remember. Definition, let this triplet F mu epsilon and still struggle with the math cal G mu prime epsilon prime be symmetric or monoidal, sorry, braided, symmetric or braided, monoidal functors. So now, a natural transformation psi going from psi goes from F to G is called symmetric or monoidal, symmetric slash, sorry, braided. Why do I keep saying monoidal? Braided, braided. So if it's symmetric, then symmetric. If it's braided, then braided. Monoidal. And I have spelling mistakes in my notes, as always. If and only if these following diagrams commute. Wow, right big. Oh, it's better for the camera anyways. Not necessarily a bad thing. Okay. So I have the tensor product of f of x and f of y, right? And the natural thing that we got used to from last time is apply mu to this to combine the x and y into one thing. Mu. So this becomes f of xy. Now, so if I apply my natural transformation on these, the tensor product of that, and I think in Lucas's notes there's a typo here. It's comma instead of psi, if I remember correctly. Y. What do I get? Well, my natural transformation takes an f and spits out g, so this is going to just be g of x tensor g of y. And now in this category, um, yep, in this category, I apply mu prime. Remember functors form a category. We talked about that last time. G of x tensor y. So mu prime takes it here, and psi of x tensor y. Right, I think this is where the typo was. There was a comma here instead of the tensor, I think. This should commute. And another condition as well. And so if I have my 1 prime and apply epsilon to it, it takes me to f of 1. Now if I do it with epsilon prime, it gives me g of 1. And my psi, I wanted to take my f to a g, and this should also commute. So these things commute. Also, let me know if I make any spelling mistakes. I can't spell to save my life, so. Okay. Now, to draw this using the graphical calculus, what do? Well, okay. I want to have f of x tensor with f of y. Tensor means I put them next to each other, right? So let me draw f of x. Now, just gonna maybe not even write down the x. We can erase that, and it's implied from the arrow being squished by these two lines. And I have f of y. So this is the top left thing that we have there. F of x tensor f of y. Now, I apply psi here. Psi on x, and this is psi on y. And so I get g of x and g of y. Now here I should use a different color. Let's do, I don't know, red or pink or whatever this is. Yeah, okay. So, gives me g of x tensor g of y, okay. So this is my x, this is being squished by g. So there's g of x, and here's a g of y. Same thing here. And great. Now, in the g category, I use mu prime. What that does, as William said, puts a cap here and joins the two things together. And what do I get? I get x tensor y being squished between g, right? So it's going to be g of x tensor y. This is x tensor y, and it's being squished by two lines. That means I'm applying g to it. So I want this. This is this path that I took, go down then right. I want this path to commute with that path. So I want this to be equal to, now what do? Now I apply mu first. So I do this thing first, then I use psi. So okay, I have my f of x here. I have my f of y here again, starting out with the same thing. Now, I apply mu to it. So I draw a cap here, combine these, get closer to each other. So this is x tensor y, and it's being squished by these two lines. So it's f of x tensor y, exactly what we have here. And now I apply psi. Psi of x tensor y. And what do I get out of that? Well, I didn't show it. Okay. I get x tensor y being squished by two lines that denote g. So it's going to be g of x tensor y. So this is the graphical calculus way of writing down that commuting diagram. And so people can see, I won't use this board because it'll be hard for people to see. Okay. And no, I don't think that's important. Okay. So this one, no, it is important. What am I saying? Okay. So what will this one look like? Well, let's do this route first. Apply epsilon, then psi 1. So we start with the unit element, unit object. So, and apply epsilon to it. Did I write down epsilon over there, what it does? Should have. Yeah, exactly. For some reason, this isn't making sense to me. But let me draw it down, then we can figure it out together. Psi S. Okay, let's see. So I apply epsilon, I get this, then apply psi, and I get that. Should be, well, it goes from F to G, that's clear. It's the same thing as you apply epsilon prime. Is that right? Like put, yeah, pink lines here and pink lines, the whole thing there. Make this whole thing pink, right? Yeah, but
Also, like over here, you have a label for epsilon, so I don't know why you won't have a label.
right. Yeah, there should be a label. I don't know whether there wasn't any labels here. Let's just add them ourselves. So my problem is that why are there two lines? Shouldn't just be. Oh, because we're not drawing one. Yeah. Okay. Thank you. Thank you. Okay. So perfect. This now it makes sense. Epsilon, right? This is giving me f of 1. We don't draw the 1, right? Perfect. And here there's a epsilon prime. Now everything should make sense. Thank you for that. Nice. Great. And this should make sense. End of definition. Alrighty. I'm going to use this in the future, so keep it here. Now, I always think I don't have enough material and then give the talk and I don't make it halfway through. The first one, I was like, oh no, I only have 18 pages of material. Didn't get even halfway through that. But I guess it's good in a way. I'll be more prepared than I need to be, which is always a good thing. So now we'll start with newer stuff. So that was a continuation of what we were doing last time with the graphical calculus and our braided monoidal functors. So now we're going to talk about the Cobordism category, the subtitle of today's talk. So the symmetric monoidal category Cobordism will denote it with board N. So perfect. So now we fix n as a positive integer. Once and for all. So this will eventually be the dimension of our cobordism, and we don't want that to change. We want to fix it and do stuff with a fixed n. Okay. Now, recall some manifold theory stuff. So a n-dimensional manifold, all denoted with MFLD manifold, or should put an n maybe, with boundary boundary denoted with partial of M is a topological space equipped with a maximal atlas or atlas locally modeled on the half space. On the half space, we'll denote it with the math blackboard HN as x, and this is in coordinates x1 to xn, elements of Rn, such that x1 is non-negative.
You lost a couple of L's, so you're missing one on maxima and in modeled. There should be 2 in modeled.
Thank you. I don't know how to spell, so yeah, I appreciate that. Okay. Now, why am I defining this? Well, it's always good to review some stuff. I usually, in physics, when you study some manifold theory, you always do manifold, closed manifolds. So you just say, right, it's locally Rn, but if you want to deal with manifolds with boundaries, which are important, you have to have the notion of a half space. If you want to work with manifold with corners, you just do the same thing, except k, the first k elements of this will be non-negative, which is a if k of them are non-negative, then it means that n minus it's a n minus k has codimension n minus k. There we go. Okay, sure. So now we say M is closed if and only if M is compact. That's just abbreviation, and it's boundaryless. So the boundary of M is the empty set. Now, end of this section. new section. Let V be a n-dimensional vector space. The frame space of V V is defined as the set of linear isomorphisms from Rn to V. Now, equivalently, f of R is a set of ordered bases of V. Yeah. Let's put that as a remark. So equivalently, it's a set of ordered bases of V. Now, the group GL and R, so end of sentence, yeah. The group GL and R acts freely and transitively on R and the subgroup of this group, the subgroup GL plus NR is defined as elements of GL and R such that has a positive determinant. So, denoted elements of GL and R, GL and R such that have positive determinant. Yes.
Let me ask a very quick question.
Yep.
Like an aside. So just trying to understand this manifold and defining it, because I'm used to like manifold in jar with like smooth and closed, and then you think of the geometry as like basically a potato, you know?
Yes.
So in this case, like this manifold, for instance, if you have the boundary of the boundary, is it empty?
Yes, it always has to be empty, yes. So I guess since now you asked about it, it gives me an excuse to go off on a tangent on this. So, right, the manifolds in the GR course, or yeah, most GR courses, especially ours, is a manifold with no boundary. So it's a closed manifold.
It might not be compact. Oftentimes it's like an open manifold.
Yeah, or non-compact, yeah. And so it could just be like Rn. And yeah, so the boundary of the boundary, right? The boundary that we use in differential geometry is the same boundary that is in homology, in algebraic topology. And once we talk about orientation, we'll see that the boundary, when we have an oriented manifold, the boundary operator maps that to another manifold with boundary. So the boundary, sorry, another manifold with orientation, my mistake. Another manifold with orientation. So the boundary canonically induces a orientation on the boundary of the manifold if we've picked an oriented manifold and a convention for outwards or inwards. It canonically does that. So we'll talk about that more, but essentially, in one of Williams' talks, he proved that. Did you prove it? Maybe you didn't prove it, but once he gave the notion of boundary at some point, he said, right, now the boundary squared is just the zero operator. Um, and the important thing is the orientation because, are you thinking if you did that or not?
I mean, I definitely mentioned that the boundary of the homology boundary operator, if you take del squared, you get 0.
Yeah.
It's kind of just like thematically similar to the boundary in differential geometry. Like it's not like literally the same.
Different boundary.
How's it different?
I don't know. One is algebraic and the other one is just a particular set of points that satisfies a condition. Whereas the condition here would be that the x1 coordinate is equal to 0.
Right, but this isn't the full thing. In differential geometry, when you do Stokes' theorem, it's really important that it canonically induces the orientation on the boundary from the oriented manifold.
Yeah.
Right, because if you don't have that boundary squared, is not necessarily 0. Right, if you have manifolds with corners, like consider the cube.
But for manifolds, I mean, you don't even need to talk about orientations to talk about boundaries, right? So the point is, if you can only have a codimension 1 boundary, then the boundary of any manifold is automatically going to be closed.
Right, the boundary is going to be.
So you don't need,
What?
you don't need orientations to have that.
No, I think it's harder to do it on the spot, but I don't think it'll necessarily be close for manifolds with corners. The reason being,
Well, you know, yeah, because we're not talking about corners.
right? Okay. So you're saying for that? Yes, for that I agree. The boundary is necessarily closed for manifolds with corners. However, it's not need not be closed necessarily. The example would be the cube. So you have the three-dimensional cube. Let's say take the boundary of that, you get the faces. Take the boundary of that, you get the edges. The boundary of that, the vertices. But if you have orientation, so you pick an orientation which is just basically it's just essentially a set of ordered bases on your manifold. The boundary operator tells you what is the canonically induced orientation on the boundary once you have an oriented manifold. And once you take the boundary again, it ends up always being 0 because of the orientation. It's really an exercise in homology that you write down the rigorous definition of a boundary and you see squaring that you always get 0. Yes.
The boundary of the cube is still a closed two-dimensional manifold.
Yeah,
It's just not visually obvious that it's smooth. That's the only thing.
Right. It's just
gonna say
yeah.
that too. I think the boundary of like there's the faces, it's like there's no boundary of it. It's still like closed manifold.
Yeah, like they still, but there's no like free edge.
Like if
The
you
edge is like,
treat it as like a CW complex, like
Mhm. Yeah.
it's still just like it has no boundary still.
yeah. That's correct.
Yeah.
I mean, if you wanted to talk about like
I think the
manifolds
yeah.
with corners in a sensible way, you'd have to have like a boundary operator that spits out the faces and the edges and the points.
Right.
So you keep track of like every level of the boundary. So every
Mhm.
time you apply the boundary operator, it like chops it down by 1. But here we're only just like spitting out all of the points where one of the coordinates is like on the edge of the hyperplane.
Right.
So it still has a topological manifold. It still has no boundary.
Mhm. Yeah, I think. Yeah, imagining as a CW complex makes it easier to see that. Yeah. Yeah. Yeah, but if you don't have the orientation, you won't necessarily get that boundary squared is 0.
What do you do? Like, you're talking about like boundary squared 0 in terms of homology, but in terms
Yeah.
of manifolds, you don't need an orientation to know that boundary
No, just in homology, right? Right, because you need the minus sign to basically give you 0.
Yeah, like when we take our chain groups, it's like you have one simplex and the simplex with the opposite orientation is like the additive inverse.
Yeah.
Just sort of force that.
Yeah,
So
exactly.
That's why that works out.
Yeah, yeah. If you don't have that, you won't get boundary squared to 0. Yeah. Nice. And yeah, I completely forgot where your initial question was.
Oh, sorry. No, I just want to like a geometrical visualization of the, because like I said, in GR,
Yeah.
the manifolds are smooth, so I'm always thinking about potatoes.
Right.
They're just fancy potatoes, but they're potatoes.
Yeah.
So in a way, just like, would this look more like the cube, or I don't know?
So here you can also imagine a potato because a potato has boundary. It's not a closed manifold, right? The potato, the skin of the potato, it's its boundary. Yeah, and yeah. So yeah, the skin of the potato is the boundary. So you can still imagine it here because we're only working with maximum codimension of one surface is. So yeah, you can just boundary of the boundary, you get fries. Maybe in with some notion of boundary, yes. But yeah, for us, the boundary of the boundary is always going to be the empty set. Yeah. Because the boundary of a potato is homeomorphic to a two-sphere, right? Just imagine a hollow sphere, right? And that doesn't have any boundary. Nice. All right. Good discussions. Uh, okay. My watch is wrong.
You say all the manifolds are like potatoes, but what about like a solid torus? Like, is that like an onion ring?
Yeah. Or a donut. Yeah, yeah, yeah. Well, of course, not all manifolds are potatoes. The manifolds we're considering here are going to be like potatoes. Mostly cylinders.
Okay.
But when we're working with cobalt. Sorry?
They can have holes?
Yes.
Okay.
Well, a cylinder, the notion of a hole isn't very well defined
But
because,
when you say it's like a potato, it invokes like there's no holes in the manifold, but you're considering.
yeah,
Okay.
yeah,
They
it can be.
are simply connected. Like, are they simply connected or?
Simply connected don't have to be because the cylinder isn't simply connected. It's connected and path connected. So pi 1 is trivial, it's connected, but it's not simply connected. Yeah.
How can it be path connected? Simply connected just means
Path connected is pi 0.
Oh,
So-
path connected.
yeah. Path connected is pi 0, connected is not disconnected.
But you can have like just two cylinders.
Can you do right? You can have two cylinders, and that's not path connected. Yes, that's correct.
I think, but
That's
every like connected component is like
Every connected
component is path connected.
yeah, every connected component is path connected. Yeah, kind of almost by definition. Yeah. Okay, nice. So yeah, most of our manifolds are gonna just look like cylinders or pairs of pants. Where were we? Okay, let V be this. Right, so this subgroup GL plus has positive determinant, has two orbits has two orbits on FRV. So now, and for I guess more about orientations, Williams H. Cobordism talk does a really great job at explaining orientations on cobordisms and how the boundary canonically induces orientation on the boundary of the cobordism uh, once you choose a convention, outwards or inwards convention. Yeah, Kevin Cosell's Chern Simons course, he does it as well. But yeah, William really goes into the details of how you do it. Yeah, both of them are online. Yeah. So, right. Definition. 22. An orientation. On V is the choice of orbit and equivalently. Doesn't matter. So, yeah, equivalently, this is you choose which order basis to call positive. I was going to write that down, but I can just say it. Yeah. But yeah, it's all in the notes, so I'll upload it either tonight or tomorrow. And I need to fix some spelling mistakes. If you find more spelling mistakes, please let me know. Um, had I LaTeX these, it would have been easier because you can fix them way easier than these type of notes. But and I'm missing a page. No, I'm not. Goes there. This goes there. Okay. 19. It's 5, right? The time? Yeah. Okay. Cool. Yeah. Yeah. I made the. I guess I'll talk about that later. Okay. Remark. And I was also going to ask about which direction do you guys want to take the lectures as well. I guess I'll talk about that at the end. I think it's more appropriate than in the middle. But yeah. 1, 2, 3. Choosing an orientation selects a set of positively oriented bases. The elements of the complement are called negative oriented. I can write that down, but yeah, it'll just take time. I'll just say. So the remark is, yeah, choosing an orientation selects a set of positively oriented bases. We talked about that. So now the complement of that, we just call them negatively oriented. Yeah. Verbally mentioned. Okay. So, start here. Let M be a n-dimensional manifold with boundary the frame bundle of M is the bundle denoted like this, f of R M on M, whose fibers over M, how do you write whose? Fibers over M over m elements of our base space or manifold is frame on manifold restricted to m an element of our base space or manifold is, there's another typo here, I believe, m elements of m. So the tangent bundle restricted to there. Now, yeah, is a principal GLN R bundle. Right. So okay, let me think about this. The tangent bundle would be specifically for the tangent bundle. It'll be the disjoint union of M and M of TPM. So you'll essentially have a tuple. First one are elements of your manifold. Second one, elements of your tangent space, right? And so if you restrict your tangent bundle to a point, what do you get? You get that point and its tangent space at that point, right?
I mean,
Yep.
you just think like locally TM is a product of manifold and Rn.
Yeah, locally you
And
can.
you're just looking at frames on that, at least locally. So
Yep.
in that case,
Yep.
it's not the same as just looking at frames on M. That's a good question. You're asking if the frame bundle on TM is the same as TM?
I think the question was, yeah, is this TMM?
Yeah.
Right. Well, wouldn't it technically be M and TMM?
Yeah, but that's the same thing.
Yeah, they're isomorphic. Yeah. So yeah, technically this is the tangent space at our point M. It's a bit confusing because M and M, but it's the tuple containing M and the tangent space at that point. But this is isomorphic to just the tangent space. So yes, you could just imagine the tangent space at that point.
Your M is like fixed, right? We're not like going over all M. We're just saying for some specific like M and M, right?
This is like for each fiber you're fixing M, but then we're actually doing this in every
No,
fiber.
yeah. I'm just like, cause like I was thinking like otherwise, like wouldn't it be like redundant to do that? Cause that's already a bundle over the whole of M, right?
This is a bundle over all of M. Yes.
Yeah.
Yep.
Yeah. Okay. But we're only like restricting it to like a single point, not like every single M and M, right?
I think it should be for all M in M, right? Yeah.
Doing
But
this replacement at each point.
Okay.
yes, but for some reason it wasn't in the notes, but I think it's technically should be that you're correct. So I'll put for all M in M. So now this, I guess a remark is a principal GL and R bundle. And I guess should do some self-advertising since we're here. William has had a bunch of talks on fiber bundles. Oh, this is horrible, the lighting, but yeah, William had a bunch of talks on bundles. The first one of which wasn't recorded, unfortunately. That was like before we started recording them. But the homotopy theory of fiber bundles, I believe, is on the playlist. So that one, he goes through a lot of the fiber bundle theory, specifically the homotopy theory of it. Yeah. Maybe we'll have another fiber bundle talk at some point. We'll see. Yeah. So
What side does the
don't know. Let me think about it. I don't know. Well, the answer is I don't know, but let me think about it.
How does it act on one of these frames for a given vector space V?
Isn't it usually like a left action, I think?
Well, you're
Well,
starting
this-
from Rn, and you're acting by self-transformations of Rn, so it's going to be an action by pre-composition. So it's going to be a right action.
Say that one more time. Is action by pre-composition?
Yeah, so like when you're acting on frames of V for your fixed vector space V, right, how are you acting by GL and R? Well, you can only act on Rn. So all you can do is act by pre-composition. So whatever your frame is going to be, your action is going to by sneaking in an element on the right, acting by the thing on
Oh.
GLRN first, and then on your frame. So it's going to be a right action.
Oh, cool.
Oh yeah, because you're applying the matrices to the linear. Yeah, that makes sense.
Very cool. Very cool. Okay. So it's a right action. Nice. Bless you. Saying it so the microphone picks it up. Okay. Yeah, I guess these are all details that should have thought about more in depth. But yeah, I wanted today at least to finish this chapter.
What's the definition of a principal G bundle again? I forgot.
I'll let you take this one because
Sure. I mean, essentially,
You're
it's
the
just a topological space with a pre-action, also that the quotient actually gets applied to bundle.
Okay.
The fibers are G, but it's they're G in a special way, and the G is actually transitively and freely in each fiber.
so now we're gonna do some examples. So that's always good. Concrete examples help us deepen our understanding. The first one is the standard orientation on R3 is determined by declaring a frame to be positive if and only if it satisfies the right-hand rule. So I'm not going to write that down. I'm just going to say it. Yeah. If it satisfies the right-hand rule, we call that positive. The frame to be positive. So now for a Mobius strip, it doesn't have an orientation because it's non-orientable. So if you pick an ordered basis, let me see if I could draw it. I actually haven't drawn it here, but I drew this one. So yeah, you have the Mobius strip, you glue these together, you get a cylinder, you take this and you twist it and bring it back. You get a Mobius strip. If you have an ordered basis, let's say this, you move this around, it comes back to look like this. So it's non-orientable. And again, William has. Oh, sorry, I drew. It's not even a Klein bottle. What is this? It is a Klein bottle. Yeah, yeah. What would it be if I did that?
You have two prescriptions.
Cool, nice. But yeah, you're right.
I guess a Klein bottle will be another example.
Right, a Klein bottle is another example. Yes, very good. And yeah, William again has more talks on non-orientable manifolds. So I refer you guys to his talks. Well, you definitely do, right? But I just don't know if they were recorded or not. Yeah. Well, I guess that's the important thing because I'm referring to. I think they were recorded. Anywho, doesn't matter. So, there are more details here, but that's not the important part. Move on to more stuff. Okay. Yeah, I try to make the notes to include everything. Yeah, it'll be there. And again, if you find mistakes, please let me know. So, another example. should I go through this? Okay, so I'll do a quicker version because I want to get to more interesting stuff. M and N are oriented manifolds, okay? And so M cross N is also an oriented manifold. By declaring a set of basis vectors, um, like this, which is an element of the tangent bundle of M cross N, begin, and such that we call that to be positive if this ordered basis is positive for V and this ordered basis is positive for W, respectively. For I guess for M and for N, respectively. Yeah. So yeah, we have a ordered a positive frame here and a positive frame here that induces a positive frame here. Yes.
You didn't actually define what it means for a manifold to be oriented.
Yes, I haven't. Yeah, I haven't defined that.
Yeah. I mean, all it really says is if, like, over each connected component of M, this frame bundle has two pieces, instead of them both being glued together by, like, twisting over the base phase. So the choice of one of these two pieces of your frame bundle, that's like choosing a continuously varying family of orientation.
Yes.
So you think
Yes.
you're kind of saying here by saying that this subgroup has two orbits?
Yeah, so for one single vector space, like, that's totally a definition, but then for a manifold, you have to be careful that your two components don't get, like, identified together as you go around the base space.
So if the frame bundle
mm.
is if the frame bundle is connected, then there's no possible choice of orientation.
Yeah.
Well, that's kind of cool.
Yeah.
I never thought about it like this before.
Say that one more time. If the frame bundle.
I never thought about like orientation like this before.
Right. But what was the thing before that? If the frame bundle is what?
Connected, like there's only one piece.
Right.
Like rather than like two separate pieces.
Mm-hmm. Yeah. Oh, yeah. That's kind of beautiful. Yeah. So if it's disjoint, then you pick one to be positive, you call the other one to be negative, and that works out. But I guess for the Mobius strip, it's connected. That's why if you take your order basis, you go around, you get the opposite orientation. That's why it's not orientable.
Those two frames are
Connected by a path, yeah. I think you talked about this in the talk that wasn't recorded. Probably. Very good, very good. Nice. Okay. Thank you. Right. So, definition. And this one doesn't have a number for some reason. But I want it to be like compatible with Lucas's. That way, if you ever refer to his lectures, you see the same number on the definitions or theorems or whatever. Let M be an orient. Well, I already said M to be that, so let M be an oriented manifold with boundary partial M. So I'm just gonna write that part down because we already said it before. The induced orientation on the boundary of M is defined by declaring a frame of the tangent bundle of the tangent space of the boundary. By declaring a frame, frame V1 to Vm minus 1 of the tangent space of your a boundary. So same thing as the tangent bundle at of the boundary of the manifold restricted to M to be positive. I'll just continue here. To be positive. To be a positive, to be positive if this v1 vm minus 1 and vm, so just add vm to the to be the last element of this frame, is a positive frame positive frame of the tangent space of M, where Vm is an element of the tangent space, is an outward pointing vector. So this is the convention that I mentioned for outward or inward pointing. We choose outward to be our convention. Yes.
You just made a typo, I guess. So you're using m to denote the point and also how many v's there are. I think you want to have n on the so v sub n minus 1.
Yeah. This was from the older notation where I was using m for this part, I guess. Continued that here, but it clashes, is clashing notation with the point on the manifold. So I'll change that to an n. And now it should be fine, right?
The one more I can't quite see from here, the v and
Thank you. Right. So nice. Now we get to the Cobordism. Definition 127. I think the last number is 130 or 131, so we're almost done with this chapter. Sigma prime be n minus 1 dimensional oriented manifolds. Oriented manifolds. A Cobordism. Cobordism M that is a map from sigma to sigma prime consists of a compact oriented manifold. You know what? I'll just do the compact oriented manifold because we're going to say this over and over again. Compact oriented manifold, M with boundary a manifold U, a manifold U containing the boundary of M, containing and right, and orientation preserving diffeomorphism from a so my boundary element sigma Cartesian producted with the half-open boundary, half-open interval, disjoint union with sigma prime. Similar thing going on here, half-open interval. My orientation preserving diffeomorphism psi is a map from here to U. And now a picture. So So this gets embedded into here, and this gets embedded into here. And this is my U, and so note that I should probably just switch back to this implies that the boundary is homeomorphic to reverse. And this is saying orientation reversing. Okay. Right. Okay. So, end of definition. Right. So a cobordism is going to be a map from our our first closed manifold sigma to our second closed manifold sigma prime, and it has the boundary compact oriented manifold M with boundary di M, and U contains di M as you see in that picture there, and there's an orientation preserving diffeomorphism side. Yes.
Now, why does it give you the opposite orientation on the left hand?
Right. Yes, because I was planning on thinking about this more, but to have time. So if U has an orientation, okay, let's say U has an orientation, and so it induces an orientation in its boundary, or boundary components, right? And it should be the opposite of the first one, because of the outwards or inwards going one. So let me draw an order basis. Let's say, so we said that's how we induce the orientation on the boundary. Let's take this, and we said outwards pointing, right? So go here. So
That's the positive orientation of one-dimensional manifold, that direction. So
it's inwards pointing.
this direction, yes, it'll be inwards pointing at the left.
Exactly.
Outward pointing.
Exactly. Exactly.
Oh,
So this is the ordered basis, and using that definition that we gave for, or like how there's a canonical, how the oriented manifold canonically induces a orientation on the boundary using our outwards convention. This one is going to be outwards pointing, so this one will be positive, and for this one it will be inwards pointing. So for that one it should be an orientation reversal, hence the bar on that. Let's, okay. Can we finish this? Yeah, not much left. We can finish this. Okay. Right. So okay, good. Example. Example 128, and then we'll be done with chapter 1. But we did start with chapter 0, so chapter 0 was pretty short. So sigma across the closed interval this time is a cobordism. Cobordism from sigma to sigma. Two disjoint unions of sigma, two disjoint copies of sigma. And so it'll just look like a cylinder, and there's a collar neighborhood around the boundaries, the boundary components. So another example, sigma across the half-open interval to orientation reversal of 0 and 1. Element-wise, what happens here is that the Cartesian product of these, so in components it'll be like x and t, go to x and negative t. Yeah. Is an or exactly is an orientation preserving diffu. Yeah. Yeah, you can just put D, but yeah. Usually, like, especially the quantum gravity theorists love to put diff as like the diffeomorphism group. And when they speak, they always say diffeos. So, yeah, just. But yeah, this is an orientation preserving diffeomorphism or diffeo. So this is still part of the example, yes. Let M be a cobordism from sigma to sigma prime, and be a cobordism there's an associated cobordism are cobordisms sigma orientation reversal of sigma prime to the empty set and the opposite direction. So this disjoint union sigma prime. And what does this look like? So you start with a disjoint union of sigma and sigma prime orientation reversed. So you start with this. There's like a color neighborhood around it, and it'll look like this. And here's the empty set, seen as a n-1 dimensional manifold. And here it's just the opposite shape of that. So just do this. Color neighborhood, blah, blah, blah. Yep. You start with the empty set, and you go to disjoint union of sigma orientation reversed and sigma prime. So, yeah.
Or you just take the cobordism and you like twist it, basically.
What do you mean by twist?
Like if you think of the cobordism as like almost like a tube, like going from sigma to like sigma prime.
Mm-hmm.
You're just
Yep.
like taking that tube and like just
Bending it, yes, exactly. Yep. Yep. So, yeah, later on when we draw the our diagrams for the cobordisms, you see that there are many ways you can look at it, going from left to right, up to down. You can bend them, whatever. But whatever we compute at the end of the day should be a topological invariant. And so, and that was the whole motivation in the 0th chapter for why we want to look at stuff that are topological invariants. Because the partition function that we gave the example of turned out to be a topological invariant. So, okay. Just 2 more pages. Right, done. Yeah, I really don't want to not finish this because then it'll be awkward resuming like today, so I want to avoid that. So, okay, definition. Yes. Let M1 and M2 be cobordisms from sigma to sigma prime, and orientation preserving diffeo relative to a boundary, relative to a boundary, relative to boundary is an orientation preserving diffeo F from our first cobordism to our second cobordism, such that this diagram commutes. So I have my collar neighborhoods again, and it's called a collar because it's like a dog collar. Makes sense. 0, 1 half open interval. Disjoint union with sigma prime. I think there should be an orientation reversal on that one that I didn't. No, it shouldn't be. Yeah. Okay. 0, so there's no typo. That's good. I have my first diffeo, my second diffeo, and this goes to my first cobordism, then my second cobordism, and my F is this map here, such that it makes the diagram commute. Okay. We're almost done. Nice. So here's an exercise. Won't write it down, just say it. The exercise is different choices of U and sigma. So sigma are diffeos, U are, I guess, you could call it the ambient space maybe. Oh, did I say sigmas? Oh, sorry, my bad. I meant to say size. Thank you. Yeah, sorry. Yeah, I meant to say size. So for different choices of U and size on the same underlying manifold are different are diffew relative to the boundary as soon as they agree on are diffeomorphic relative to the boundary as soon as they agree on sigma reversed disjoint union sigma prime. So this is telling us that's the boundary. That's the boundary there. The boundary of U is, where I wrote it somewhere, here. This is the boundary. So for different choices of U and psi on the same underlying manifold M are diffeomorphic relative to the boundary as soon as they agree on the boundary of M. So essentially, the only thing that matters is the boundaries. So this is what matters. And we'll consider equivalence classes of cobordisms if they give the same boundary at some point. Okay. Now we want to see, because in the category theory part was important for us to, when we have morphisms, we always want to compose them. So we'll talk about how to compose cobordisms, because we'll eventually see that they're monoidal, a symmetric monoidal category. So let M1 be a cobordism from sigma to sigma prime, and M2 be a cobordism from sigma prime to sigma double prime. Do you guys have a name for double prime in English? In Persian, we have something called, I think, zigond or something. I don't know. Do you have such a name? You just call it double prime, triple prime. So nice. Yeah, for some reason in Persian we have names for double prime and triple prime. B, cobordisms, and we define the composition of M1 with M2 as follows. The underlying topological space is this. So I'll just write it down. M2 composed with M1 as these cobordisms are the disjoint union of these, but then we glue them together in this way. So our first diffu applied to the point x Cartesian product 0. So our time one in our unit interval is 0. No, no, no. Yeah, not at all. Okay. How's this? For all x in psi prime. Sorry, sigma prime. I'm horrible at multitasking, so I always say something wrong like that. Sigma prime. Yes. Okay. So, yeah, we have this cobordism going from sigma to sigma prime, then this cobordism going from sigma prime to sigma double prime, and we glue them on sigma. Well, the diffuse is applied to elements of sigma, to be exact. And so note that there's a diffeomorphism. No, oh, this is a long definition. Okay. 223. I will. I will. Yeah. Let me see. I can skip. 1 second, sorry. Note, I'll just say there exists a homeomorphism onto its image. Sigma prime across a different interval, an open interval. So it goes to the composition of our cobordisms. And so what this does element-wise, in brackets, I'll write it, it takes an x Cartesian product t, and it maps to our first diffu acting on x cross t for negative time. It doesn't have to be time, but we'll kind of treat it as time. It's just t is just an element of the interval. That's it. And our second diffu applied to x cross t for positive t. Okay. So Let me draw a picture, as William said. I have this. Right. So this is sigma prime, this is sigma, and sigma double prime. Okay. So what's going on here? I have the disstring union of these. This is my M1, this is my M2, and I'm gluing them on sigma prime. So what will happen here is that the open interval around sigma, let me just glue them first, becomes like so. And we had our colored neighborhoods around sigma prime. So let me draw those with the red. That in this picture becomes the sigma prime cross the open interval from -1 to 1. So this becomes that. In that picture. Right. And what psi does here takes in elements of sigma prime. X is an element of sigma prime written here, times t, some element here, and maps it into here. So let me draw that. So some element, let's put it here, right? Sigma prime cross t, some t. Psi maps that. How do I draw this? To somewhere here. Psi 1, this is what psi 1 does. And psi 2 does the same thing here. Yeah. And at the 0, where's the 0 when t is 0? This, it's just sigma prime. They have to agree. That's where the gluing is happening. Okay. Any questions? Okay. So, I should maybe skip this. Let's see. We define the smooth structure on the composition of M2 and M1 by taking the maximal atlas containing charts for M1 set subtract sigma 1 prime and M2 sigma prime and M2 set subtract sigma prime and sigma prime cross the open interval. So
The entire point of choosing the colored neighborhoods is that we get a smooth structure.
on the
That was like the whole reason.
right. Yeah. Yeah, so by having the maximal atlas on M1, but without M1 without the sigma prime, and M2 without the sigma prime, and this colored neighborhood around sigma prime, we have now a smooth structure on the whole thing, on the composition. Okay. So yeah, here's I guess a remark that the smooth structure depends on the choice of color. Two choices are diffeomorphic to each other. The orientation at a point is induced from either M1, M2, or the color, right? Because let's say M2 doesn't have an orientation, right? And sigma, the color here, sigma prime, doesn't have an orientation. If I have a orientation here, let's say this is my orientation, we talked about this, that it canonically induces an orientation on sigma prime, and hence the color, because we mentioned for the Cartesian product of two oriented manifolds, there's an orientation. That's also an oriented manifold. So now we have a orientation on the color, which this induces an orientation on M2. So the whole thing becomes oriented. So if I have an orientation on either one of these three things, either M1, M2, or the color of sigma 1, it canonically induces an orientation on the entire thing. So that's nice. Yes?
It's still possible that like M2 has a component that's like in a separate path component from where the sigma prime integral comes in. There might be another piece of M2 out there somewhere.
Oh, so like a disjoint, a non-connected component,
Yeah.
disconnected component, right?
So at least like on the connected components where you have this color identifying them, then yeah,
Yes.
for instance, like you can use an orientation on one of the pieces and give the other two.
Yes.
Then you might just have something unrelated hanging out somewhere else.
That's completely correct. Yeah. So I'll just say for the mic, yeah. What I said is true for all the connected components to this collar. So if M2 has some, let's say, a cylinder here, it doesn't canonically induce a orientation on there. But on the path connected components to the collar, it does. Very nice. Very nice. Okay. Okay. Nice. Nice, nice. Last page. Awesome. Awesome, awesome. I didn't want to erase that, but so I learned from Williams drawing skills, how to draw donuts and glue them together. The red one's good chalk, eh? Like it's pretty visible.
It's good on like the board. It actually doesn't show up very well on the video.
Really?
Yeah.
Oh wow.
Don't know why.
I think it's because it's the fluorescent one. I'll use the other one. You should. Oh, okay. It looks really good in person for, I guess, the audience. Sorry if it doesn't show up well for you guys. I think it's just because I picked the fluorescent one. Okay. But is it somewhat visible at
It
least?
kind of just looks white. Like it's a little bit different from white. It mostly just looks like a white.
Oh,
It's okay. Like I
Okay.
think people can tell that it's
People-
not exactly the same.
okay. Okay. Well, for the people watching the video, sorry about that.
I don't know if it would be easier if you also do your green, a neon green. Purple.
Yeah.
More distinguishable.
Yeah. Okay. We're almost done, anyways. So, definition. 130. The symmetric. Just right. Symmetric monoidal category. Board N. So n-dimensional cobordisms, we'll write it like that. Board N has objects are closed oriented n minus 1 dimensional manifolds. Dimensional manifolds. So these are the objects, right? And our morphisms are equivalence classes of cobordisms up to diffuse relative to the boundary. To the boundary. And I think it's denoted like this. Correct me if I'm wrong, William, but I think it's denoted as diff restricted to boundary on them. This part I'm not sure of, but I saw it in a talk somewhere. That's why I wanted to write it down. I wanted to see.
Seen diff subpartial. Like if you have two manifolds that have the same boundary, you can just say like diff subpartial is diffeomorphisms that.
Oh yeah, I think you're right. I think it was that. Yes.
Or even just, I've seen it leaving the M off because you haven't introduced any other M's, so it's kind of confusing to have that extra symbol that hasn't been discussed at all.
Fair, but we discussed it there.
Okay.
Yeah, so I'll justify that we discussed it. But yeah, boundaries are yeah. So I'm not completely sure on this notation, but I think it's true. But take it with a grain of salt. So our compositions, right? Always the composition of our Holmes matter in our category. So composition is gluing. That's nice for people interested in differential topology. This is fun. So it's not just abstract category theory, but there's some diff top here. The unit at sigma is the equivalence class containing the color neighborhood around sigma. The monoidal structure. So the monoidal structure, I have so many spelling mistakes. The monoidal structure, so I'll just give you the monoidal product, or the generous tensor product, whatever you want to call it. Let's just call it the tensor is, here it's the disjoint union. So yeah, this might seem a bit crazy to write, but it actually makes sense. And so the unit one is in this category, the one in the cobordism category, board N, is the empty set. And my empty set in my notes looks like a phi, so I'll try to write it better here. As this is important, as an n-dimensional manifold. Yeah. Yeah, I myself said n-1 here. It should be n-1 here. So I guess that's a typo in the lecture series of like the Lucas one. So yeah, it should be n-1, yes. As a n-1 dimensional manifold. right? Because objects, we said, are n-1 dimensional manifolds. And what else? The braiding, fitting here, the braiding is, okay, let's do this. So I take the disjoint union of sigma 1 and sigma 2, and I take the color of that, okay, and there's an injection into this of sigma 1 disjoint union sigma 2. Right. And sigma 2 disjoint union sigma 1. It injects into here with braiding that looks like this. Braiding of sigma and sigma prime looks like I have two disjoint unions of sigma, call it sigma prime, sigma, and just and this is sigma and sigma prime. Okay.
Your interval looks like a half of an interval. I think that should be a closed interval.
I think so too.
Because it has to be a manifold, compact manifold.
Yeah. Yes. Yes. It should be. Yeah. I agree. I was thinking the same thing. I don't know if this is my type. Well, definitely my typo, but I don't know if it was in Lucas's course as well or not. But yeah, should be close. Yeah. Thank you. I was thinking about that. Sorry for going over time. Exercise proved this is a symmetric monoidal category. I haven't proved this myself, so this is an exercise. Didn't have time to prove it, but yeah, it is. You can trust me that this is a symmetric monoidal category, but definitely try to prove it using the axioms that we talked about in the last talk. Now, the very last thing that we're done is that now we know what a TQFT is, because remember in the first talk, or the 0th talk, I guess you can call it, because it was chapter 0, we said what a TQFT is, a symmetric monoidal functor from the Cobordism category to vect category of vector spaces, but and now we actually know what these words mean. So that's great. Right? We said that now we know what a TQFT is, up to knowing what like a symmetric monoidal functor and all these category nonsense is. It's no nonsense, but it's abstract sense. So let's see be a symmetric monoidal category. A TQFT with values. So back to Atiya's definition, with values in C is a symmetric, symmetric monoidal functor, functor Z from the category of cobordisms and dimensional cobordisms to this symmetric monoidal category. Now, the most common symmetric monoidal categories C for a TQFT are usually the category of vector spaces denoted as vect, or supervect, which is supersymmetric vector spaces. So you include bosons and fermions as the physical reason. So yeah, C. So usually C equals vect or supersymmetric vect, SUSY vect, sometimes written as S vect. And this is what a TQFT is. And so now we know what a TQFT is, and we're done with chapter 1. So yeah, that's that. Sorry for going over time.
Yeah, the recording itself is like exactly 2 hours.
Oh, you just finished it?
No, not yet.
Oh, okay, okay.
Wait
Yeah, wait for questions. Any questions? Yeah, so I'm interested in this, seeing this supersymmetry stuff here. I, for my definitions of, I've always seen it as vect, but I want to see both fermions of bosons show up. So yeah, essentially the equivalence class of cobordisms up to the boundaries being the same thing just tells us the important things are the boundaries, because another version of this is, I guess I've seen people talk about it. I haven't seen it in this series yet, but instead of vect, they consider Hill, which is the category of Hilbert spaces. And in there, that's essentially where your wave functions live, is in your Hilbert space. So that's like the physically important thing, not really the cobordisms. That's just becomes your unitary transformation, I guess endomorphisms on your Hilbert spaces. That's your operator, your unitary operator, a map from the Hilbert space to itself, to a Hilbert space. And so yeah, essentially yes, the boundaries, the tensor product, the generous tensor product of Hilbert spaces, generous tensor product, by that I mean the monoidal product. The monoidal product for Hilbert spaces is the tensor product. That's like the physically important thing that you should care about. And that's why we say the equivalence class of cobordisms up to diffuse relative to the boundary. Yeah. Yes.
Yeah, throughout the talk I was also wondering why we cared so much about the equivalence classes of these up to boundary. First I thought it was just because we wanted our HOMs to actually be sets instead of every possible cobordism. But really it's also so that we can actually have actual units. So like the cylinder, sticking it on the end, if you had just random cobordisms, like sticking it on the end, it's not literally equal to that manifold, but you get a diffeomorphism relative to the boundary.
Yes.
So I've seen cobordism categories in different contexts where they're like embedded cobordisms. So everything is embedded into R infinity. So in that context, you actually don't have units, but you don't care. You're like, we don't actually need units for any of the constructions we're doing. We don't care. But I think for like everything we're doing here is symmetric, monoidal, blah, blah. You actually really want to have units.
Yeah.
So I think that's important to have that equivalence relation.
Yeah. Yes. Yeah. I would imagine so too. Yeah, I haven't give that specifically much thought, but yeah. Yeah. Thank you.
Because like having units gives you
Oh.
states, I think, or something like that. Or like, yeah.
Okay. So it actually does correspond to something physical. I mean,
Because like cobordism from the zero-dimensional vector space, like you're mapping a zero-dimensional vector space to some dimensional vector space is just a choice of a vector in V. So that,
right.
that's like the cobordism between the empty manifold and the
No, okay. Yes. Okay, to add on to that, yeah. I remember Lucas gave a separate TQFT job talk at some point, and it was like Right, because the whole thing was initially motivated by the partition function in QFT, and so what that is a map from C to C, C being the complex numbers, and a map from C to C itself is C. C is a map from C to C, which is kind of cool, and right. So for us, C would correspond to the unit, the TQFT functor applied to the unit of the cobordism category, right? Which is the empty set, right? You apply the TQFT functor to the one in the cobordism category, so the empty set, where you end up is an element of the field of your vector space. For us, we'll take to be C, so it's going to be a map from C to C, which is what was our initial motivation to study the topological invariance of the partition function.
So which is C?
C is the field of the vector space.
Yeah, yeah. But you said Z applied to something. Z applied to.
To the unit in the cobordism category, so the empty set. Because what it'll look like.
The zero vector space.
Yes, which is that not C?
Zero vector space. I think it would just go to the ground field.
Oh, I see. Because it has to be the unit for tensor products.
Yeah.
Okay. Okay. Okay.
And the unit for tensor products is?
It's
C.
C.
Right, C. So it should be C. Yes, that makes sense. And so, yeah, and because, yeah, in the motivating talk, we were like, right, so if I have some shape, which will essentially probably be some gluing together of some donuts, and I want to, and this gives me a partition function. So the partition function, this is the partition function, will be a map from here, which is C, this zero vector space. It's going to be C, and it's going to be mapped to C here. And so this turns out to be a topological invariant, this partition function in QFT. Yeah. So yeah, now we know what the definition means of a TQFT. Any more questions? Well, you think of questions that I was going to ask the direction of where the talks you guys want to go. So something I can try to do is give like 1 or 2 bonus talks on this. Try to just continue the series as much as I can in preparation for the Atlantic TQFT 26 summer school. I'll leave on Sunday, so yeah, the summer school is next week. We can try to do that, and I'll try to give like send the email like a day in advance, so people get notified. At the very worst, like the morning of. We can do that if people want. It'll also be good practice for myself as well. Another thing is that, yeah, I'm thinking of, I was talking to Francisco, who gave the talk on the Witten-Morse theory paper. And think of starting like a sub-series of wonderful works of Witten, which we go through some of Witten's important papers. Pedro at Perimeter did something kind of similar to that. Had a beautiful papers course. One of them was obviously Witten's Jones polynomial and 2 plus 1 DTQFTs. So I think that would fit very nicely to this whole story, because we also saw the knot theory, under and overcrossing stuff and the braiding happen in especially the previous talk. So I think it'll be very nice to see that, and that's why he won the Fields Medal amongst other reasons. But that was the main paper, so I think that would be nice. And kind of to Francisco mentioned that he would want to do the rest of the same Morse theory paper. The Suzy QM is Morse theory paper. Do it for like the QFT stuff.
I wanted to talk about
The sigma, the Witten sigma genus, yeah. There's that. So there's definitely interest. I'm interested in both the Jones polynomial and 2+1D TQFTs and the index theory stuff. So the famous, as every school child in quantum field theory knows, the number of generations of chiral flavor fermions is tied to the topological index of an elliptical operator on a Calabi-Yau manifold. So that's equation 4.2 of Witten's vacuum configuration for superstrings paper. And there's, of course, if we're talking about interesting Witten papers, we'll be here for the entire night. But so there's definitely a lot to do. So I was thinking of starting that sub-series. And if anyone is interested in presenting anything of Witten, definitely feel free to join. Yeah, of course he is more physicsy stuff, but we'll focus more on the mathy stuff that he's done.
I think he could have some of his older stuff. It was a lot more mathy. Right? Like now he's got quite a bit of physics, but yeah.
Yeah, so try to do that, and yeah, Francisco also said he'll give some talks on the topological string theory stuff that Kevin gave a course on, because that has a lot of like derived symplectic algebraic geometry, which is pretty cool. So yeah, but yeah, if you have any suggestions about that, let me know. But I guess we should, if there's no more questions, we should end the recording.
Okay.
Yep.